Okay, so we can summarize the diffusion model on this slide. So there are three critical stages of the decision making. First, detectors in the empty area detect information about the motion. So next, integrators or decision-making neurons in the area LIP integrate this information over time. At the same time, these neurons inhibit alternative decisions. And finally, if the activity of one of these integrator reaches a decision-making threshold, it activates the motor neurons in the area FIF, in the frontal eye field, and animal switches the gaze in the same direction. So we see here a very basic fundamental model of the decision making. So why do we need these inhibitory connections between the integrators? I think it makes sense to have this stage, and I would illustrate you this idea by two models. So if we remove the inhibitory connections, we actually would see a so-called race model. So according to the race model, decisions can be programmed independently. So imagine that decisions for alternatives, for different choices, can be actually programmed by independent neuronal populations. So they can collect sensory evidences independently, and the first most active decision-making neuron will win the race and will activate their motor neurons. So in this case, there are separate integrators that accumulate evidences for alternatives. In the diffusion model that I just presented to you, actually this network compares evidences for alternatives. So inhibitory connections between integrators actually allows a comparison between the evidences for decision A and decision B. Many models shows that actually diffusion process is more effective and quite often faster than race model. Let's summarize the race model and diffusion model. In the race model, choice is made as soon as the integrated evidence in support of the one alternative exceeds this threshold. And in this case, different choices are programmed independently, and the fastest process wins the race. But in the diffusion model, the decision is finalized whenever the difference between the evidences for two alternatives reaches a threshold. So this model actually is sensitive to the differences between the evidences for alternatives. So let's make a look to two hypothetical situations. In these situations, there is the same amount of evidences for the right side motion, but the different amount of evidences for the left motion. For the race model, it doesn't make a big difference. According to the race model, animal will make a choice to switch gaze right. It will make their choice with the equal speed in the situation 1 and situation 2. Simply because the decision-making process, the accumulation of information for alternatives, is independent. According to their diffusion model, animal will make choice faster in the first situation, and decision-making neurons will achieve the decision threshold faster in the first situation because the network in the diffusion model calculates the difference for the evidences for alternatives. So I would illustrate this adaptive mechanism here. So neurons, decision-making neurons, according to the race model, will gradually increase activity proportional to the evidences for the alternatives. For the situation when there is no conflict of alternatives, and for the situation when there is conflict of alternatives. Basically, the fastest neuron will win the race, and since this neuron is not affected by the alternative, the reaction time will be the same in both conditions. Whereas in the diffusion model, the decision-making neuron compares evidences for alternatives. So when there is a clear difference in the evidences for alternatives, this neuron, this neuronal network, will achieve the decision threshold faster than in the situation when there is a conflict of alternatives, when alternatives are close to each other. So diffusion model reacts adaptively to the levels of evidences supporting the alternatives. And this adaptive mechanism is not present in the race model. So it looks like it is more effective to use the diffusion model. And actually, what do we see at the brain level? Perhaps neurons actually use the diffusion approach. And importantly, the diffusion model can produce faster decisions. So this is a relatively simple model, but this model helps us to understand various aspects of decisions. If we will see the decision-making process as a diffusion process, for example, we can explain our decision biases. So what is a bias? It can be simply a difference in the starting point of the diffusion process. Imagine that neurons are pre-activated, and in this case, the accumulation of information will be faster because simply neurons will reach the decision threshold faster. It can be that the information is processed more deeply, so we are more careful with the processing of information. And it would mean the slower accumulation of the activity of the decision-making neurons. So in this model, it is called drift rate. So in this case, if we are slowly and more slowly are processing the information, the drift rate will be smaller. Sometimes, perhaps, we can be ready to make decision very quickly with some costs. So we can even make some mistakes. In this case, we can even lower this threshold for the decision making. So this simple model can help us to explain various aspects of the decision-making process. So actually, the diffusion process can be implemented very differently at the level of the brain. So here I show you three different designs of the neuronal networks that can actually implement the diffusion process during the decision making. So you see here that actually already detectors, so for example motion detectors, they can suppress alternative decisions. Alternative integrators accumulating information for alternative decisions. Or we can imagine that actually integrators or decision-making neurons can inhibit each other, can inhibit alternative decisions. We can also imagine that there is a third-order neuron or a network of neurons that actually weight activity of the integrators. So very different designs can lead to the same outcome. So perhaps at the brain level, the diffusion process can be implemented differently. But right now, we have some evidences that actually nervous system performs the diffusion-like calculation during the decision-making process. So we can summarize this model on this slide. So the sensory evidences are accumulated, processed by our detectors in the sensory system. The next, decision-making neurons, integrators, integrate information from the sensory neurons over time, inhibit alternative decisions, and whenever activity of these integrators reaches a certain threshold, the decision is finalized and information is transmitted to the motor neurons that actually trigger the behavioral response. So this is a very important model in neuroeconomics. It suggests that decision can be split in few stages. So first, for perceptual decisions, for this particular task, there are motion detectors, they are located in the area empty. So next, the information goes to the LAP area, and neurons here integrate information from the motion detectors, and whenever activity of the LAP neurons reaches a certain threshold, they activate frontal eye field that actually triggers the motor response. It switches the gaze in a certain direction. So if we will make a look to this decision-making neurons in the area LAP, they accumulate information from the motion detectors, they gradually increase activity, the firing rate, and if this firing rate crosses this threshold, the decision is finalized. If the firing rate of this neuron doesn't cross this threshold, the alternative wins.